Hello, 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 Cheska. Hello, Avani. All right. Hello, and good afternoon, Yavi, and good afternoon, Michelle. Awesome. All right, we're gonna get good afternoon, Matthew. Good afternoon, Avani. Oh, double shot. All right. Okay, here we go. Awesome. Who did I say? Yes, good afternoon, Yavi. Good afternoon, Matthew. Good afternoon, Avani. Double goof afternoon, Marilyn. Okay, I shouldn't say. Did I say Michelle? Oh, both Michelles. Is this the first time I'm realizing there's well, I know both Michelles. I don't know if I realized they're both. I know both Michelles. Anyway, all right, whatever. I don't think I realized that they were both. Anyway, okay. Good afternoon, Hayu. Good afternoon, Malita. Good afternoon, Michelle. Good afternoon, Freddie. Okay, Chris. Oh, another Pokemon. I mean, not that that is the easiest. Okay, hi, Chris. Okay. I mean, Pikachu. I mean, electric type, really? But okay, no. All right. Okay, this is not the time to talk about Pokemon, even though it always is. Oh, Eevee. That's not Eevee. Oh, you're saying you like Eevee better? Yes. I mean, who? Yes, who did? Right. Okay, got you. I mean, we won't get into whether it's which evolution. We won't talk. All right. Anyway. All right. No, we can't. Okay. We cannot. Oh, and now he's going video. That's great. Thank you all, video people, Cheska, Michelle, Lavani, and Chris, and thank you, Avatar person, Michelle. Uses it. Okay, that's funny. Oh, here we go. Oh, I forgot it was this class. Okay, but I'm not gonna. So here's the deal. Okay, so we've got this Espeon. Yeah, I like Espeon actually. I never even got it. Was like ESP because it's psychic ESP. Okay, anyway. Eventually I got it. Of course, it took me years to realize Pikachu was a okay. Stop. All right, so here's what we're gonna do. I'm gonna talk sort of quickly today. Charizard. Okay, stop. Okay, Charizard. That takes no creative. Okay. Well, who doesn't love Charizard? Of course. Stop. Okay. Here's the deal. Oh, hang on for a second. Wait. Serious moment of. No, okay. Yeah. All right. Here's the deal. We're gonna do the same thing I did in the morning class, but there was a reason I'm saying that. What we're about to do in a second, I'm going to. Okay, I'm not looking anymore in the chat. I am going to go somewhat quickly through the following problem. I'm going to change my. Oh, okay. I'm going to change the screen share in a second. Oh God, everything's happening at once. We're going to go to one of the last and thickest and biggest, most important problems in homework 7. I'm going to skip straight to a big problem in homework 7, which is the same type of problem as a very important and thick and challenging problem in your exam, in your practice exam. I'll make it clear. Okay, bear with me for a second. I'm going to do screen share so you'll know what I'm talking about. But basically, you'll recall that you have this practice exam that you never turn into me, but it's just for practice. And you'll recall that your actual exam will be very, very similar to your practice exam. Anywhere that today or Wednesday, anywhere that I give you direct solutions, direct answers directly to something in your practice exam, then I would tweak those things slightly onto your when I make the real exam. But anywhere that I don't directly address something in your practice exam, it probably is going to appear very much identically, pretty much like the same way, maybe exactly the same way on your actual exam. This means a number of things. This means, number one, as somebody in the other class pointed out to the whole group, and I'm glad she did, there's tons of old videos online, my old videos, where I walk through problems from old practice exams or old exams that are extraordinarily similar to yours. That is more than fair game. Like, I'd be delighted if you guys find those old walkthroughs and you share them with one another. Anywhere you can get information about this practice exam, please do. Anything you can do to make this practice exam easier for you to understand it, please do. And please know that if you find things on your own from past semesters of mine, but I don't like literally do it here, then all the power to you. It may appear, I might even appear with the same numbers on your exam. I don't know. And I don't care, because again, you're going to show me that you understand on your actual exam. So all that, so please go for that. It just, yeah. That said, what I want to try to do today and Wednesday is walk through particular things that I think are particularly related to your exam. And anything that if I do an exact thing today or Wednesday, okay, then I might change the numbers. So what? Or, change certain details or order, sequences of things. But again, I'm going to tell you that if you can rock this practice exam, if you know the practice exam inside and out, and you do 3 drafts of it on your own time, then no matter what changes I make to the actual exam, they won't be big enough for you not to rock that. I can tell you that. Where I'm going with all of this is that, sorry, I'm getting myself slowed down, is that in a minute, I'm going to do a screen share to show you what problem from homework 7 that I'm about to walk through. And I will tell you that it is exactly the basis for a problem on the practice exam that even refers to it. There's a problem on the practice exam you could turn to right now that says something like the Pontiac and Toyota revisited, or something like that at the top of it. And so I'm going to do the Pontiac and Toyota right now. I'm doing it on purpose that way so that you still have something to practice on your own, before you take the actual exam, but they're the same problem. Just bear with me for a second because I'm getting myself. But it'll take me almost all period to walk through it. Hold on. Sorry. Just bear with me for a second. Then Wednesday, I'm going to continue essentially doing this, walking through things that I think will help you with the practice exam, or therefore the real exam. But on Wednesday, I'm going to try to do two totally different problems in the 2 different classes so that you can watch the video from the other and get twice as much material for your investment. I'm trying to do many things at once. So I would encourage you if we do this fast enough, if I get going fast enough, and I'm going to be going fast so that you can ask that many more questions on Wednesday, or that you can ask me that many questions today about what I'm doing. But I will warn you right now that probably asking me totally unrelated things that are unrelated to the problem I'm doing, I probably won't have time for today. Hold on. So today is going to be about this one problem that's big in the practice exam, and then Wednesday I'll do at least a different one, and then there'll be one more that I do in the other section. So you watch the video, that'll be at least 3 of the big problems on the practice exam. Okay, one second. So I'm just trying to get the screens correct here and the video is correct. Bear with me for a second. And if there's something in the chat right now, bear with me. I can't see it just yet. Hang on one second. Okay. So that's that. All right. What I will post to you what I'm about to do. I'll screen share to you what I'm about to do. Is there something in the chat already? No, there isn't. That's good. Okay. Just so you see what I'm doing, and you can screenshot it or something if necessary, though hopefully you have it. Okay. So what I'm about to walk through is this problem from homework 7. It's page 5. It says relative, I don't know, it's part of the relative velocity vectors in depth thing. It's part B. Okay, so I'm skipping right now straight to this problem in homework 7, where what you have to do is add 2 two-dimensional velocity vectors. That's what's happening here in this problem, is you're taking 2 two-dimensional velocity vectors and adding them together. And again, I'm switching the screen share now for a second. Again, I shouldn't be doing this, but what that's exactly like, just to be clear, or what it's the practice for. I don't know why this didn't save from before. Sorry. What this is exactly like, for those of you who are not clear on this. Is this all happening on your screen? Yes, it is. Okay. It's exactly like this problem right here, free float. Like in effect, I'm about to do this problem for you now, only I'm leaving the actual thing itself for you to actually practice, okay? But this is what I'm about to show you how to do. And the other two, there's a couple other big problems in the practice exam, obviously, like for example, this one, but this one I will do on Wednesday in one of the two sections, okay? And like basically this one I'll do in this one right here, I'll do in the other section. So hopefully there'll be time for other kinds of questions that you could ask on Wednesday in class, but that's the deal but I think these are the biggest things you need to see in order to rock this exam. Okay, so all that said, I'm going to go to this problem right now. Bear with me for one more. I was going to switch screens and start solving it. Bear with me again. I know I just walked away. The summary of this, all right, is everybody cool? Can I switch screens back to like the drawing screen? And thank you, Cheska. Okay, I'll take that as, although I say that and I never do this correctly. Okay, here we go. Here we go. Okay, so we're now going to go back to, oh, we're good. Okay, so we're going to go back to the notes. Now, let me just, the overall sum is this. What I'm about to do, this problem, adding two two-dimensional velocity vectors, you'll hopefully see as you're following me do this, computationally, the computational procedure that I'm about to do, the math, is identical to what we did on Wednesday when we added two displacement vectors as an earlier problem in this homework 7. Like, in fact, I think the numbers might even, I mean, the objects are the same. It's like a Pontiac and a Toyota and a gas station. The numbers might even be the same. That's all fine. The meaning of what we're doing here is completely different. And that's and that's what you sort of have to practice or think about, is that Wednesday, we learned what it means to add vectors, particularly two-dimensional vectors. The whole idea is that vectors are easiest to picture when they're displacement vectors, when an arrow on the page has a certain length, and that length represents a certain distance, a certain length in real space. So like whatever we did Wednesday, you'd like maybe a 2-inch vector is representing like 2 miles of space in the real world, okay? What we're about to do now is use the whole principle of vectors is that whatever we do with them works for all different kinds of vectors. So we're going to put arrows together and add them by the same component method today. But the arrows that we're putting together today don't represent lengths over space. They represent instantaneous velocities. So each arrow that we draw on the page now, like the longer it is, means that some object is going that much faster at a certain instant in time. You could think of the instant in time as being represented by the tail point of the vector. So I just want to say this one more time, because this somehow this throws, this is a more abstract representation. It throws people off. When I draw a long arrow on the page, that does not mean that anything in real life has traveled far. There will be nothing about what we say today that will indicate in any way how far anything has traveled. We have no idea, because in the problem that we're looking at right now that you just screenshotted or whatever, like this Pontiac Toyota problem we're about to look at, it never says anything about time at all. It never tells us how much time any of these cars or whatever have been traveling. It's the whole thing is one snapshot, one moment in time where different cars are going at different rates of speed and in different directions at that moment in time. So a long arrow on a page will mean a car is going very fast at that moment, okay? So you have to be considering that when we do this. The whole real issue today is like, what is it? Is constantly trying to remind ourselves what it is, what it means that we're doing, what it is that we're trying to picture, and ultimately then, the real trick of today that you want to pay attention to, especially if you are following the numbers, is like, how did I know which vector to add to which vector? How do I know when to add velocity vectors or when to subtract them? And the answer is what's written on the board right now. The answer is that this entire problem that we're going to do today is the application sort of many of us have been waiting for. This is, excuse me, this is an application or a concrete example of what we mean when we say GPR form number 4, case number 3. When we say Galileo's principle of relativity as applied to 3 objects, when we say VAC equals VAB plus VBC, what we're telling ourselves is which kind of velocity vectors can be added to make what, or conversely, which kind of velocity vectors can be subtracted. It all depends on what velocity is relative to what. So like that's what you want. So I'm going to start right now. Of course, I'm going to talk fast again so that I can like get through this and so I can leave room for more questions at the end or for Wednesday. But it doesn't mean you can't stop me and ask questions. I'm speaking fast so that there can be questions, if that makes sense. Okay, so you should stop me if you don't understand what I'm saying. But the main thing to be looking out for is today we're applying the concept of how velocities work in the physical world to the mathematics of vector addition. That's what's happening or about to happen. So as soon as I pause one more moment. What's my printer just ran out of ink. Okay. So let's, why did I do that? All right, so let's go. So I want to go. Why can't I change the page? Okay. So yeah, so we're going to homework number 7, page number 5, relative velocities in 2D, it's called, aka adding velocity vectors. Again, the other thing is, if you feel like you've already done this, probably, if you're following what I'm saying, my best advice, like as I go, my other best advice is like have the the free float problem out next to you too, the one from the exam. Like see if you can follow what I'm doing in the context of, or take notes on that problem. That's really what this is about, for what it's worth. But okay, so this is about, as I just said, VAC equals VAB plus VBC being applied to the mathematics of vector addition. Okay, so first we go to, so the first, it gives us a fact pattern in the problem. And I'm trying to do the 5-step method here. I'm pretending I'm you taking an exam. So first I draw a diagram of the situation, right? I draw the 2 vectors that were given to me, or I give you the 2 velocity informations that were given to me. First of all, I was told that a Pontiac is going 30 miles an hour at 30 degrees northeast relative to a Toyota. Right now, there's many ways a problem could phrase that, like on an exam or in life. Like the way it said it was something like the velocity of the Pontiac relative to the Toyota. I don't remember, but it could. Oh, it says a Pontiac travels at blah 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 relative to a Toyota. Another way it could have said that, it could have said compared to a Toyota, or it could have phrased, like switched all the words around. It could have said like from the reference frame of a Toyota, a Pontiac travels at da-da-da-da. Like, don't be thrown off if on your exam, the whole sentence is like moved around. If it says from the perspective of the Toyota, a Pontiac travels at blah, 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 or it says from the perspective of a Toyota, blah, 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 or in the coordinate system of or a Toyota measures a Pontiac to do blah, blah, blah. All of those different ways are all different ways of saying that the Toyota is the basis of comparison. It's you are like the first sentence of the problem is basically saying you're driving the Toyota, you're playing a video game where you are the Toyota and you're the first person, like the hero of the video game, and you are looking out on the world and you see a Pontiac going in some direction at some speed, right? Like the first sentence is telling what the Pontiac is doing from the perspective of the Toyota. So if I let T stand for Toyota and I let P stand for Pontiac and I let G stand for gas station, as I made up my little legend in my little diagram that I'm making, then the first piece of information they're giving me is V VPT. Order does matter. VPT means Pontiac relative to Toyota. It means Toyota's perspective looking at the Pontiac. One last thing, it means that the Toyota regards itself as stationary, like you would in a video game, in a first-person video game. And it's making measurements on the Pontiac, right? Okay, so VPT is a vector going 30 miles per hour at 30 degrees north of east. Hopefully you know what I'm saying. So it's like relative to east. Like there's like that dotted imaginary brown line going off to the east, and the 30, you get what I'm saying. So then I'm giving this other fact, this other observation, which is what the Toyota is doing relative to or from the perspective of the gas station, right? Now that's a completely different perspective. It's just like a totally different arrow. I'm just drawing it somewhere else in the page. Again, it does, I can draw wherever I want in the page. Please understand that VTG arrow that I've now drawn it's like twice as long as the first one. If I'm very careful, if this is really my exam, maybe I actually did get out a ruler and try to make this arrow maybe twice as long as the first one, right? And maybe I even used a protractor to make these angles. I mean, I didn't, but maybe you should. And notice this other arrow is now what the gas station sees. It's a completely different perspective. I hope that's clear. Like there is no one person, there is not any one observer or person or coordinate system in the world that's literally, nobody in the world thinks that the Pontiac's going 30 and the Toyota is going 60. I hope that's clear. Like the first arrow is from the perspective of the Toyota. It assumes that the Toyota is at rest and the world is going by the Toyota. The second arrow assumes that the gas station is like sitting there while the world goes by it. Okay, and those are the two facts we're given. Last two things on this. Obviously, I'm going to speed up in a second, but notice the two angles are like independent of each other. One is 30 degrees north of east. The other one is 20 degrees south of east. The 20 degrees is not 20 degrees from the first arrow, if you see what I'm saying. Okay, so those are the facts that I'm given. I just drew, and I drew a coordinate system, like making clear, like, okay, on this axis from here on, anything up my page is called north. I mean, is what I mean by north. Anything down the page is south. I'm going to call anything going north positive. I'm going to call anything going south negative. That's a choice. It's not obvious until I tell you that that's my choice. And then independently on the other axis, I make a choice about what is positive and what is negative. So I've got all those facts there in my step 1 DFP. Wait, I'm just gonna, sorry, I'm going back and forth between screens. So if there's something, I'm sorry. Okay, I was just gonna say, Melita, sorry, I didn't see your hand because I was looking at the other screen. Go.
All good. You said that like the order of the letters is important. That's like what you're talking about. Like what you mean by that is like if you do VPT is not the same as VTP.
Exactly. Exactly. Right. Oh, sorry. Wait. Sorry. Did you say something after?
I just said thank you.
Oh, okay. Okay. You're welcome. No, that's awesome. And no, it's a great question. And we're going to see that specifically, like, in fact, I think, yeah, down at the bottom of the page or in the first question, like, I'm totally right. I mean, it's exactly what Melita said. I'm not saying that VPT has nothing to do with VTP. Like they're very related, very related. We'll see at the bottom page, but they are different. Yes. VPT means what P is measured to be doing according to T, and the other way is the other way. If I say VTP, that's what T is measured to be doing according to P. And guys, everybody, like not just Melita, this whole relativity thing, like it comes in layers to all of us. Like at some layer for everybody in the room, it's like so obvious, it's almost doesn't seem worth talking about. But then we always hit a layer, everybody. I mean, this includes all instructors. This includes me. There's some layer that, I mean, this is why Einstein, you've heard of Einstein's relativity. Like relativity is a big deal always through physics. And there's some level at which it becomes really advanced and surprising to everybody. But what I mean by that is, if any of you is already thinking, as I draw these two arrows, I do VPT and I draw VTG, or you read the facts and problem, if anybody of you is thinking like, okay, fine, like that's what the Toyota sees the Pontiac doing. Okay, fine, that's what the gas station sees the Toyota doing. But like, what's really happening? Like, if any of you is thinking like, okay, but like, where's the arrow for what the Pontiac's like actually doing? Or like, who cares what the Toyota thinks? Can't we just get to what the Pontiac's like actually doing? Some of you might be thinking that, and it would not, you shouldn't be ashamed if you're thinking that. And it doesn't mean you're stupid or anything like that. But I'm going to address it in a moment. But similarly, some of you might be thinking, okay, one of these arrows is what the Toyota sees, but the other arrow is what the gas station sees. So, like, obviously, like, if I were standing in the gas station, like I'm standing still. So whatever the gas station sees is like really more true. You might be thinking that. Maybe you're even thinking it without thinking you're thinking it. What I'm here to say, what I'm here to drum into everybody's mind is no, 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 no. The whole point of all these subscripts is there's no actually anymore. There is no actually correct perspective. The Toyota's perspective is just as legitimate as the gas station's perspective. And if you think the gas station's perspective is more legitimate because it's like attached to the earth, which it might be, like, sure, the gas station might be stuck to the ground. And the Toyota is like not stuck to the ground. It's like moving along the ground. That's all true. But there's nothing special about being stuck to the ground. If you're stuck to the ground, that means you're stuck to the earth. And in third grade, everybody accepted the idea that the earth wasn't sitting still either. The earth is like hurtling past the sun at 65,000 miles an hour. I'm not trying to be weird. I'm trying to say that these problems are trying to emphasize that everything is a matter of perspective, and every one of these perspectives is just as legitimate as every other. So this is all, I'm just playing off Melita's question. I'm not saying anything's wrong with Melita's question. So we're going to do some math now in a moment. But I want you to know there is no arrow that tells you actually what anything is doing outside of perspective. There's no outside of perspective. Everything is a perspective. Okay. And no one, by the way, is necessarily saying that the gas station is like actually still. The gas station could itself be a gas station that's like on a motorhome that's going by the highway. Maybe it shouldn't even call a gas station. Maybe it is a food truck. And maybe the food truck is driving. I have no idea, and it doesn't matter. Okay, anyway, whatever. So Melita's right. VTP is not the same thing as VTPT. So therefore, when the first question asks, the very first question, the first question asks, what is the velocity of the Toyota relative to the Pontiac? Okay, I'm saying what that's really asking is what is VTP? And we were not given VTP, and we were given VPT. Now it's asking for velocity. So I wrote it here at the bottom, like step 2, what's the question? The question is VTP. And this is kind of like a warm-up question, one of a couple of warm-ups for the big thing that happens. But it asks me for the velocity of the Toyota relative to the Pontiac. Well, velocity means vector. It's by asking velocity, it is, by definition, asking me for a speed and a direction, if you know what I'm saying. Like, if this were in the exam and I just wrote 30 miles per hour or something, I would not have fully answered the question yet. Velocity means it means vector, and it means magnitude and direction, and we're in 2 dimensions now, so direction is going to mean an angle with points of the compass. So I've got to provide all of that to answer this question. I'm not saying it's hard, but I'm just saying be careful. So how do I do it? Well, my step 3, GDP, is what he calls rule number 2. I call it case number 2. He, the guy that wrote the sheet, he calls it rule number 2. I call it case number 2. It is, and I'll write it even more clearly here. The actual thing, the actual GDP, the actual GDP itself, you know, I probably wrote in the class originally is something like VAB equals negative, as negative VBA, right? Now, people do get the A's and the B's and the C's and the P's and the T's. Like, for some people, like, their head is swimming with all these subscripts. What I'm trying to tell you is, when I originally said with A, B, and C stood for any 3 arbitrary objects. Like, A, B, and C could mean anything. So it's kind of like X, Y, and Z in algebra or something like that. They just stand for whatever letters we're ever going to put there or whatever objects. So the original thing I wrote as like the general principle is VAB equals negative of VBA. This is to address Melita's point. What this means in general is if you, and again, just go to the video game thing. If you see me going at 50 miles an hour to the north, then if you think about it, I hope you'd agree that I see you going 50 miles an hour, but to the south, right? Like this is the way it always is in life. The only new information here is I'm telling you that we're both right. You might have thought up until now that like one person was like suffering an optical illusion or something and the other or something. I don't know what you thought, but I'm saying both of those perspectives are correct. If the sun sees the earth going 65,000 miles an hour to the west, then to the east, then the earth sees the sun going 65,000 miles an hour to the west. That's the nature of velocity. So here in this case, to move on to get the answer here then is VTP must be the opposite. There should be a negative sign right there. VTP must be equal to negative of VPT. Therefore, the answer here is that according to the Pontiac, the Toyota is going 30 miles per hour, the same magnitude, 30 miles per hour, but in the opposite direction. So at 30 degrees southwest rather than northeast. This goes back to something Chris sort of clarified last class. Like, what's the opposite of northeast? The opposite of northeast is southwest, because every two-dimensional quantity is really two one-dimensional quantities happening simultaneously yet independently. So if you want to flip northeast, you flip the north and you get south, and independently but simultaneously you flip the east and you get west. So the answer here to this sort of warm-up, whatever, is GPR number 4, form number 4, case number 2. This is just showing us how velocities work when there's two objects. But then the next question, I'm just going back to the Zoom answer questions. Okay. The next question then is, okay, what is the Toyota doing? Relative to the Toyota. It's just really making sure that we get this concept. And the concept is GPR, form number 4, now case 1. We used to write it, or I wrote it originally in Electra as VAA, triple equals sign 0. If there's only one object, I don't care what object it is, call it A, or in this case, call it a Toyota, call it T. If there's one object, then what one object is doing from its own perspective, how fast something is going relative to itself, is always 0. I can never run away from myself, no matter how hard I might try. Right? I can't say any, but that's the essence of relativity. Everything is stationary to itself. Everything else is moving to the self, and the self is moving in the opposite direction to everything else. So, okay, so the answer to here is 0. Stop me if that's not clear. But now we get to the real issue. Now we're going to get to the hard part. I think the comparatively hard part of GPR, form number 4. The hard part is case number 3, when there's 3 objects involved. Now that's what we have here. We have a Toyota, we have a Pontiac, we also have a gas station. Now, again, honestly, the more I think about this, or the more I talk about it, it's almost unfairly deceptive that we call the gas station the gas station. That really makes it seem like somehow the gas station is special, because it makes it seem like the gas station is like sort of actually sitting there while everything else is moving. That's really, really not like counter to the point. So, in fact, I think in your exam problem, I'm just going to check really quickly. Hopefully in your exam problem, it's better than that in a way. I'm just checking really quick. Well, in your exam problem, something similar to that is going on where there's water and there's a boat and there's a riverbank. So you might really think that the riverbank somehow is special. It's not. An ideal, and maybe on your actual exam, maybe I use the exact same numbers from the riverbank problem, but maybe I change the riverbank, boat, and water into 3 pool balls on a pool ball table. I've done that before, right? You got to realize that these 3 objects, they all have an equal legitimate perspective on the world. So here in this case, back to the problem, here in this case, we're asked, what we're ultimately asked, wait, where am I? where we're ultimately going to be asked, as you see, we're going to be asked to draw things and solve for what the Pontiac is doing from the perspective of the gas station. Like, that's what nobody told us. We know what the Toyota sees the Pontiac doing, and we know what the gas station sees the Toyota doing. The question is, if you were standing in the gas station, what in the heck would you see the Pontiac doing? That's what we're being asked here, right? That could be that. So we have to do something with these velocity vectors. Maybe we have to add them together. Maybe we have to subtract them. I want to say very definitively right now, that is your job to figure out on the exam. Like, you're going to be somewhere in this exam, you're going to be given two velocity vectors, and somewhere you're going to either add them or subtract them. I'm not telling you in advance whether you have to add them or subtract them. Or put it another way, I'm not telling you necessarily which two you have to add to get which third. How that may seem as a surprise. Like, it may seem, I don't know what that seems like, but like, how do you know which ones to add or to get? Well, the answer is GPR form number 4. Like, the thing I'm trying to drum in here is what we know it for all time. Like, it's written on the middle of the page here. We know, bring it all back to subways. We know the velocity of me relative to the subway plus the velocity of the subway relative to Manhattan yields equals the velocity of me relative to Manhattan. AB plus BC equals AC. And again, back to Melita's thing, like, the order totally matters. What everybody knows in the simple one-dimensional case of subways, we all know what I just said is true, I think, if you think it through. But it's easy, and hopefully that's easy to remember. But it's easy to remember and easy to comparatively easy to remember and easy to believe and easy to picture, because in the case of subways, first of all, it's one-dimensional. Second of all, at least one of those numbers is 0, right? I stand on the subway. I go 0 relative to the subway, while the subway goes 8, or I sit. 0 relative to the subway. The subway goes 80 relative to the streets. Therefore, I go 80 relative to the streets. That's why I take the subway. Hold that in your mind and remember it forever. But what we're saying now is that what makes this physics is believing and realizing, oh my God, that's still going to be true, that concept, even if none of the numbers is a 0. And someone asked me that this weeks ago. Even if none of the numbers involved is a 0, and even if we're in 2 dimensions, so everything looks all cockamamie and the numbers don't add easily. That's what's going on here. If I'm going to get the Pontiac according to the gas station, then I'm going to add Pontiac to Toyota plus Toyota to gas station. That's what's going to happen here. And if I want to add those velocities and their vectors, I'm going to place them tip to tail. So I'm taking the velocity concept of relativity and applying it to the vector computation operation of tip to tail components. So here we go. When on the problem it asks, like in the exam, when it asks now, I think we're, oh, sorry, now I'm back to the wrong thing. Oh, when it asks, yeah. All right. So it sort of drags it, whatever, my colleague who wrote this problem, like it says, first, it says to like carefully draw the vectors and apply GPR4, rule number 3, to find, oh, it does say to find the approximate speed and direction of the Pontiac relative to the gas station. Okay, and then it gives you the steps. The steps are what I just did right here. Like, it has you draw the vector for the VPT. Well, it doesn't tell you which. It tells you to draw a vector and then place it tip to tail with another vector. And that's what I'm doing. And the way I know which ones to put tip to tail with which is because I know PT plus TG will give me PG. And that's what it's asking for. It's asking for the approximate speed and direction of the Pontiac relative to the gas station. So here's my picture, right? Like, again, I can't emphasize enough. This is exactly what we did on Wednesday of last class. In terms of the computations, it's just what it means now is very different. But so I made one vector, and then from its tip, I started the tail of the other vector. And so the answer, the sum of the 2 vectors, the vector that I'm looking for, VPG, would be the red long arrow that completes that triangle. This is how vector addition works, no matter what the vectors mean. So how I knew which vectors to put together was from GPR. How to put them together comes from vector knowledge. So I did that, and the problem in the test actually asks me to look at my picture and sort of estimate an answer. It says find an approximate speed and direction of the Pontiac relative to the gas station. So I did. So like, here's, if you are doing this exam or whatever, and you really use a ruler and a compass to create this triangle, then if you measure the third line, the red dotted line in the triangle, and use a protractor to measure that last angle, your estimates, your approximate answers should be darn close. They'll provide a really good check. I mean, if they're not exactly spot on with what all of our analysis is going to show. That's how vectors work. If they're actually drawn carefully, then the drawing will get you the answer. So here's my drawing, but I didn't use a ruler and a compass. So I estimate. So just looking at my drawing, it seems to me that VPG, the answer I'm looking for, is like approximately 65. I mean, it's an estimation. In other words, I think it's like a little bit longer than 60. Notice, I don't think it's 60 plus 30. I don't think it's 90, right? 60 plus, even though I'm adding a vector that's 30 to a vector that's 60, but they're vectors, they're in funky directions. If they was all in one straight line on a number line, then sure, 30 plus 60 would equal 90. But 30 going like this plus 60 going like this, especially if the angle, if they're very close to not if they're very close to perpendicular, then I think the answer, the sum of them, is going to be only a little bit bigger than 60. So I guesstimated 65. And the angle, and what angle do I mean? I mean the angle between the red line and an imaginary horizontal, an imaginary reference line that points east, right? The angle that I'm guessing here, where I say 7 degrees southeast, that's what I mean. How much south is the red line from the eastern horizon? All right, so that's my guesstimated answer based on my drawing. That answer is like what the problem is asking. Now I'm going to go back to Zoom because I can't see. Am I in it? Oh, okay. Oh, funny. Okay, that is funny. I'm going to ignore the joke. Just going to go, but that is funny. Yeah, actually, that is actually. It's not just funny. Actually, that is clever. For what it's worth. Okay, I'm not going to dwell on it, but it actually is an insight. We're about to get components of vectors, and a lot of textbooks and a lot of websites will ask you to picture these components or ask you to suggest that the way to understand these components are as though they are shadows. Like that is actually a standard helpful comparison. I'll be more explicit about that in a moment. So, all right, what I'm going to do now, so good point though. What I'm going to do now, I'm going to get the actual answer. I'm going to compute, I'm going to add the vectors analytically by the component method. Let me be super clear about something. For some weird reason, when I look really closely at this homework 7 problem, so I don't think anywhere in the homework 7 problem, it actually comes out and asks you to do this, which is kind of funny. And I kind of never noticed that before. I mean, I didn't personally write this problem. So please don't be confused about what I'm about to do. The problem just had you draw the diagram and guesstimate the answer. I guarantee you your exam is going to ask you, I guarantee you your exam is going to ask you to actually analytically get the answer. So I'm going to do that now to show you what's expected of you. If you didn't do it on the homework, you won't lose any points because the homework didn't actually ask, apparently. But I don't want to confuse anybody now, all right? I am now going to solve the problem analytically because I guarantee you that is what happens in the free float question of your practice exam, and it is what's going to happen in your actual exam. So I'm now, as it says at the bottom of the sheet of the board, it says, let's analytically compute the answer now. We're going to compute, we're going to see how accurate our sketch is. We're going to compute velocity of VPG, the velocity of the Pontiac as observed by or as measured by the gas station. So we're using the component method for addition of vectors. This method, once you understand it, it works for any kind of vector. So what do? What is the method? The method is we zoom in individually on each vector. So I'm going to take each vector that was given and I'm going to break it up. Like I'm just looking at it on its own. Hello. I'm sorry. I'm going to look at it on its own. So first I'm looking at that VPT vector, the Pontiac relative to the Toyota. It's going 30 miles per hour at 30 degrees northeast. So I break it into its components. I say, I let you the brown lines. And notice there's arrowheads, there's tips and tails on everything I'm doing here, and there must be in your exam. Do not, one surefire way to show that you have been paying attention in this class and that you're with me, one surefire way is that every triangle you put anywhere in your exam is all consisting of arrows. Do not just write triangles that just have sides that look like geometry math class triangles. I mean, I'm just telling you, like it's one thing the whole purpose of this is to track directions. So here, this triangle, what I'm saying is northeast is really the sum of some amount east plus some amount north. Then that's true of any kind of vector quantity. So for example, if something right at this moment is traveling in a northeastern direction, like I don't know how far it gets, I don't know how much time we're looking at, but I just know at this moment, it's like facing northeast, it's driving in the northeast direction from the perspective of the Toyota, then that means at this moment, it's going somewhat east, while at the same time, it's going somewhat north. And those two components, those two portions, those two fractions, if you like, together add to make the whole, right? So I'm adding east, I'm drawing an arrow to the east with a tip at the end of it. And from that tip, I'm making an arrow that's going up to the north. And I'm saying the sum of east plus north makes northeast. And I'm trying to find out just how fast am I going to the east while I go to the north at just how fast of a speed. So that's what I'm about. So I'm going to find these components. Now, just quickly back to what I think Chris said. These components really are real, okay? This is not just like raw geometry. We're trying to figure out, basically another way of saying it is if you have a car, if I try to figure out the legs of this right triangle, and it necessarily is a right triangle, the whole procedure of this is every vector I'm ever given, I treat as the hypotenuse of its own right triangle, because I'm getting how fast it's taking us on the x-axis while how fast is it taking us on the y-axis. It's really like two cars are doing those independent things, but at the same time. One way you can picture it is like, just to affirm what Chris said, like if you had a pole sticking up there at a 30-degree angle to the northeast, if you shined a light from above, you shined a light that was just pointing straight down south on that pole, the pole would cast a shadow on the ground. We're trying to find how long that shadow would be. That's the x component of this hypotenuse. Similarly, if you shined a light from the left, the pole would cast a shadow on the wall. We're trying to find out how long that shadow is. Those shadows are known as the projections. Like you could call, a lot of textbooks and websites will call these components the projection of the vector onto each of two perpendicular axes. And projection is another word for shadow, in effect. So anyway, I know it was a joke what he said, but it actually is an insightful joke. So that'll teach you. Okay, so how do I get these two components? I'm just looking at the time. Okay, how do I get these two components? Well, I'm doing SOHCAHTOA, and I'm skipping steps now, because like I showed you on Wednesday, you want to practice on your own. But in math class, when you learn SOHCAHTOA, I'm skipping steps on the piece of paper. I'm going to say it now once to remind you. In a math class, when you say SOHCAHTOA, you're generally assuming that you know the sides and you're getting an angle or you're getting like the trigonometric function of an angle. We generally here at this step, we're going backwards. We know the angle. We're trying to get the sides. So if the sine of the angle equals opposite over hypotenuse, we just skip to the chase. We cut to the chase every time in physics and say, fine. If the sine of the angle gets you opposite over hypotenuse, then the opposite side, then in my mind, I'm multiplying both sides by hypotenuse. I'm saying that and I'm just going to do that every time. The opposite side from an angle is always going to be the hypotenuse times the sine of the angle, right? So PTY, how fast the Pontiac's going along the y-axis is 30 times sine of 30 degrees. sine of 30 degrees is 1/2. So it's 30 times 1/2 is 15 miles per hour. Notice when you think about it that way, you may or may not have ever thought about this in a trig class or a math class, but the point is that sine and cosine are always just fractions, right? They're always numbers between 0 and 1, or -1 and 0. They're always less than 1 in magnitude. So what sine and cosines are they're fractions. They're like percentages. The sine of the angle tells you how much of the hypotenuse will be projected onto the opposite axis, and the cosine tells you how much of the hypotenuse will be projected onto the x-axis, onto the adjacent axis. The bigger the cosine is, the smaller the sine is, and vice versa. Like, if you really think about it, they start actually making sense, sine and cosine, or at least they do to me, once I'm seeing them in this physics context. Each one of these legs, I will move on, I promise, but because we're going to do this like 4 times, I'm not going to re-explain it 4 times. But each one of these legs is some portion of the overall vector. So we're dividing the overall vector into how much it really means or represents or does on each of the 2 perpendicular axes of space. So VPTY, we're saying, is like 15 miles per hour. VPTX is 30 times cosine of 30 degrees, and cosine of 30 is like 0.866. Keep your calculators in degree mode for this kind of thing. So VPT is approximately 26.0 miles per hour. So what that means, and these are miles per hour, right? This whole thing is happening at an instant. All of this is just an analysis of the Pontiac and what the Toyota is measuring the Pontiac to be doing at some given instant. At some given instant, the Pontiac is going 26 miles per hour to the east while it's going 15 miles per hour to the north. That's what the Toyota is seeing it do. And the Toyota is not wrong or right. It's just the Toyota. So, okay, so those are the 2 components. Now, that was just an analysis of the first vector. I just put those numbers, those results in my head or on the paper. They're just sitting there now, and I move on to the other vector, right? Okay, so I'm not adding anything yet. There's no addition happening yet. I now look at the other vector, VTG, the velocity of the Toyota relative to the gas station. So this is now the gas station's perspective, looking at the Toyota. I have no idea. And if you want to know what the gas station sees, if it's looking at the Pontiac, that's what we're ultimately trying to figure out. But here's what the gas station sees looking at Toyota. I do the same method. I zoom in on the individual Toyota vector, right? It's long. It's like twice as long as the other one. It's 60 miles per hour. Again, it just means that's how fast the Toyota is going at this moment, and from the gas station's perspective. And at this moment, it's going in the southeasterly direction. So now I try to find its components. So I say that southeast is some amount east plus some amount south. Now, notice I keep saying that. If you're really, you might be noticing that every time I say like southeast, I then say southeast is some amount east plus some amount south. You might say, wait, why does it keep doing that? Like, you might think it's a typo, or like, in other words, you might be thinking, why can't I say southeast is some amount south plus some amount east? Good question. I could say that, but there's a reason I'm not. I'm going to take a quick pause to give you, like, can I add a page? I don't know how to add a page. Wait, do I know how to add a page? I don't know how to add a page. All right. Yes, I do. Hold on. No, I don't know how to add a page. I'll figure it out. Sorry, this is what happens. You get a new. I don't know how to add a page. Okay. So right here, I'm just going to quickly, like, when I say southeast is some amount east plus some amount south. Could I say it the other way? Could I draw it the other way? If, just quick example here in a different color. If I had a southeast vector, I have to break it. This is where you really need to practice, because what I'm doing here is the right thing. You don't realize until you practice how many choices I'm automatically making here. And like, when you practice, you realize there's a lot of other ways that you could do this, and you don't see why some way is better than another until you practice them. So for example, if I draw a southeast vector and then I divide it into components, I could say that southeast is some amount south plus some amount east, right? I could say that. That would be true. And then here's my right angle right there. I could do that, but I'm telling you right now, those of you who are listening, don't do that. like you could, it seems reasonable. And it's what a lot of people will just do if they're doing something for the first time. But the problem with doing that is then this angle here is not the angle that we were started off with. That angle is not a southeast angle. That's an east-south angle. That angle represents, that angle is being measured from the vertical. Okay, and I'm not saying you couldn't do that, but then you're going to get, then everything is like, all the numbers are different from, mean something different from what you think, from what the numbers were given in here. And your ultimate answers are going to be like backwards of what you think they are or what they're supposed to be. I don't want to confuse people anymore. What I'm saying though, first of all, I'm saying practice. But second of all, I'm saying, if you'll know you're doing things correctly and strategically if you're always measuring angles from the horizontal, so that all your directions are always like south of east or north of west or whatever, and they all sound like normal English. If you're ever measuring an angle from the vertical, you're departing from like what, I don't think you're doing what you probably want to be doing. So you want all your angles measured from the horizontal strategically. So my advice is always draw a horizontal first, and from the tip of the horizontal, make the tail of the vertical. That's advice. I'm not saying it's the only correct way. The whole point of Galileo is just more, but I am saying if you're at all tentative with what you're doing, or unless you're 100% sure, the safest thing is always to draw horizontals first and then verticals, which is why I'm saying over and over again that southeast really means some amount east plus some amount south, because I'm in the habit of always drawing my horizontals first, so everything is in reference to the horizontal, and you'll know you're doing it right. If every time you have an, because let's be honest, my 9-year-old son always says, let's be honest. For a lot of us who are doing SOHCAHTOA a lot, like last year or two, whatever, for a lot of us, the weird thing about SOHCAHTOA is like, it all makes sense as long as someone tells you which angle to look at. But for a lot of us, the confusion is like opposite of which angle, adjacent to what angle? How do I know which is like the correct angle? I don't know if you've ever been in that, but I used to be in that confusion. And probably I didn't even really work it out when I was a student. I probably just like forgot about it and just prayed to, did a Hail Mary every time I tried to solve a problem. If you can relate to what I'm saying at all, that you never really knew what they were talking about, like which angle, what I'm telling you right now is if you do vectors with arrows, you will know you're doing things correctly. If every time you have an angle that you're talking about, it's the angle between the tails. If the angle is the angle between the tails, like of two vectors, and one of them is horizontal, not vertical, then you are doing things properly. And that's another good reason to keep all your arrowheads in. I'll go back to the problem now, but that's huge strategy and advice for anybody who's sort of getting what I'm saying, but like wanting to do it perfectly. Make sure you always draw horizontals first. And as you're going, checkpoint yourself. Are my angles always between tails? And are they always measured from horizontals? If so, I'm probably doing something right. Okay, back to so here we go. So here we have this other vector that I'm zooming in on, VTG, right? So I've got VT, so I'm dividing into two components, a horizontal one and a vertical one. And I'm finding out those two components or those two shadow projections or whatever. So what are they? The adjacent side is hypotenuse times cosine. The opposite side is hypotenuse times sine, right? So I write out those numbers. Those are, I do them on the calculator. So 60 times cosine of 20 is approximately 56.4. It's a small angle, so it's very close to a high percent. So it's a very high percentage of 60. Then the other one is 60 sine 20, so it's a very small angle, so it's very small percentage of 60. So the other one is 20.5 miles per hour. So what we're saying here, we now we have the independent components ready to be added. We're saying now this triangle, I'm like yelling so much that the dog is going crazy upstairs. The dog really wants to learn physics. But he doesn't have the calculus prerequisites. So this diagram means that from the gas station's perspective, the Toyota is going like 56.4 miles per hour to the east, while it goes at the same time, in that moment, it's going at a rate of like 20.5 miles per hour to the south. That's okay. So we now know, we've broken up the PT vector into independent XY pieces, and we've broken up the TG vector into independent XY pieces. So now, and only now, we can add. The whole purpose of all of this has been to add these two vectors, But but as you learned in lab 3, or as you saw yourself in lab 3, X can only be added to X and Y can only be added to Y. Like we only know how to add numbers on a number line. So I go to the next page and I make an XY chart where I literally divide the universe into two independent physical worlds, like a horizontal. Oh my God, Ivani looks so, she's like, yeah, I got it, dude. Okay, no, sorry. All right, I'm sorry. I shouldn't do that. But yeah, so we got the anyway, the horizontal, the VX world, and the VY world. In each one of those independent worlds, we're going to add VPT to VTG. Let me again caution you. What if I wanted to put a twist on the exam, or if I really wanted to separate those people who really understood what was going on from those people who were just sort of like blindly copying stuff? Not that I would ever want to do that, but if like that were, then what I might then on the exam, I might give you all this kind of information, but I might say something on the exam like the Pontiac is doing this relative to the gas station, and the Toyota is doing blah 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 relative to the gas station. What's the Pontiac doing relative to the Toyota, right? Like I could do that just to warn you. I could give you this type of thing, but I could say, I could give you in effect VPG, and I could give you VTG, and I could ask you in English, I could ask you, what's VPT? I'm going to say it one more time. I mean, you definitely maybe want to make a note of this. I'm saying I could give you whichever ones I want. And if I gave you two velocities that were both what the gas station saw, but I asked, what is like the Pontiac see the Toyota doing? If you would realize that would be subtraction, not addition. Because if you write it down like VPT plus VTG equals VPG. So if I asked you, like, if I gave you two other terms and asked for the third, maybe you're expected to subtract from both sides and make it a subtraction problem. Does that change any of the work we've been doing up until this moment? Not at all. It would just mean that right here where I have a plus sign, you would then know to put a minus sign. Okay, I'm just going to say this one last time. Like all of the stuff we're doing here is just vector manipulation, vector addition, as we learned on Wednesday. But how do you know whether you're adding or subtracting with velocities? You know because you write down and examine GPR form number 4. GPR form number 4 tells you what could be added to what, or put one final way. If I ask you vector and you need to know, well, which two vectors should I add together to get that vector? You know from writing down GPR form number 4. It tells you what kind of problem it is. Then you do all this vector stuff. So now, okay, but this one is addition. So now here I am in the chart. I'm adding VPT to VTG in order to get VPG, right? So I add the numbers. I notice, however, one thing. Okay, I am boring everybody now. I'm boring myself. I'm not really though, because I'm screaming. So I'm really excited. I'm just adding the numbers. But notice one of the numbers is negative. Where did that come from? Why is that? Because like VTG sub Y is negative, because if I look at the VTG triangle, the Y component was going south, not north. So I'm looking at all these triangles, always whatever direction they're going in matters. That's the one, and that one was going south rather than north. So that got a negative. So everything else in the pictures was going north and east. So I'm just looking at the chat. Oh, cool. And he does that when he knows that I think he's bored. Then he like throws in something to like make me feel better, which is very humane. So we compare the X. Yeah. You only relate X to X and you only relate Y to Y. That's so the whole thing about this. Yes. A two-dimensional problem is really two one-dimensional problems happening independently but simultaneously, right? It's all like basically what you were realizing in lab 3. The whole thing is that everybody knows this in lab 3. The reason you could do lab 3 without knowing any of this is like, this is true when it comes to walking. What people don't realize is that it's just as true when it comes to, when it comes to distances, it's true, but it's just as true when it comes to speeds. That's what we're saying. So yeah, the X velocities can only be added to X velocities, and similarly with the Y's. So all the work we did up until this moment was to break up our vectors and get individual X pieces and Y pieces. So now, yes. So now, yes, we're going to use arctan. And in fact, if that's a polite way of saying that I should get to the arctan, sure thing. Yes, we are. Okay, so here we go. So, okay, so we're just about done. What we now know, yes, we're going to use arctan, and we're also going to use Pythagorean theorem. Because what we now know on this page, and yes, we're almost done. What we now see on this page is, in the final analysis, what the gas station sees the Pontiac going 82.4 miles per hour to the east, while it's going 5.5 miles per hour to the south. So overall, what is the Pontiac doing? What is the Pontiac doing? I make one final right triangle. Everything is right triangles. I make one final where I draw my horizontal first. I go, okay, it's going 82.4 miles per hour to the east. So tail to tip. And then at the tip of that horizontal, I start the tail of a vertical, and it's going 5.5 miles per hour to the south. And again, these are all representing instantaneous rates of motion. So I put them together and I say the overall sum of these tip to tail vectors is the hypotenuse, which is going some amount at some number of degrees southeast. How do I get that amount of that hypotenuse? Oh, and this red hypotenuse, the reason that it all becomes red now, I mean, it's the answer, but this red hypotenuse is like the zoom in, or this is like the zooming in on that red arrow that we have in our original diagram of all of this, right? That was a sketch, a prediction of what we think the final answer is going to look like. And here is the final answer. Now, notice it's long, like we predicted, like longer than 60, certainly. And it's going in a southeastern direction, like we predicted. Our numbers were just predictions, so they're not exactly right, but the scales were right. So we do Pythagorean theorem. We say that the length of this hypotenuse is the square root of the sum of the squares. So it's like square root of 82.4 squared plus 5.5 squared. So this hypotenuse is approximately 82.6 miles per hour. Now, it's not a lot longer than 82.4 because that 5.5 is so small compared to 82 right? This is like, my diagram is like kind of not to scale. Really, this is a very long, thin triangle where it's mostly horizontal. It's only a tiny bit of a vertical triangle. So the hypotenuse is barely bigger, but it is bigger than the horizontal leg. And then the angle, yeah, totally what Chris said. The angle, I'm skipping a step. I'm saying tangent of the angle of theta equals opposite over adjacent. And that's true, right? TOA, like tangent of theta equals the opposite side, the vertical side, over the adjacent side, the horizontal side. But I don't want the tangent of the angle. I want the angle itself. So I have to undo that. I have to go backwards. I have to do the inverse function. On my calculator, I would hit tangent to the -1, or in other words, what Chris is correctly calling the arctangent, or what you might call the inverse tangent. I want the inverse tangent of the opposite over the adjacent, 5.5 over 82.4. So I get approximately 3.81 if my calculator is in degree mode, and that's 3.81 degrees southeast. How do I know southeast? Because I'm taking my picture seriously, because one of those arrows is going east and the other one's going south. So that final red arrow is somewhat south of the eastern horizon. So my answer is 82.6 miles per hour. So the answer is the gas station sees the Pontiac, observes the Pontiac to be going at 82.6 miles per hour at 3.81, approximately 3.81 degrees southeast. This is what the gas station sees. Even if the gas station is like on like an ocean, like it's a gas station on an ocean liner or an aircraft carrier or something that itself is moving in the ocean, I don't care. Like, I have no idea. I know now what the gas station is doing relative to the Pontiac. It's the reverse of this. I know what the gas station is doing relative to the Toyota, But what the gas station is doing relative to anything else in the world, I have no idea. And I don't care. It doesn't affect any of this. And if you want to know what the gas station's actually doing, then you're asking the wrong, then there's no answer to that. Hopefully you're seeing me, that I'm saying that over and over again. So this is the answer to VPG. I'm going to go on now. There's 5 minutes. I'm going to go on and say, just give you a little, well, there's a little bit more to the problem. Before I do the little bit more, the bird's eye issue stuff in the, now again, I just got answers that the problem didn't like literally ask for, but your exam problem, the practice exam problem does, and your real exam problem will. But let's just say, just to be clear, say someone's like really insistent, but what's the gas station doing? Or someone insists, but the gas station is actually sitting still, right? And I keep saying, no, it's not actually doing anything. One thing I could tell you is what the gas station's doing from the perspective of the Pontiac. What it's doing from what the Pontiac would see the gas station doing is exactly the opposite of what the gas station sees the Pontiac doing, i.e., right, this is back to case 1, or excuse me, case 2. The gas station is going 82.6 miles per hour at 3.81 degrees northwest, like the opposite of what the Pontiac is doing according to it. So that's not a question in the sheet, but I'm just telling you, just to be clear. Then what the sheet asks is, I mean, what the homework 7 asks is, well, can we now draw some bird's eye views? Now, this is interesting. This means now, like what we just saw for was one particular vector. We just saw for what the Pontiac is doing from the perspective of the gas station. But the problem is asking, does the gas station still, like, is the gas station only concerned with the Pontiac? Does it only see the Pontiac? No, that's just what we've just being asked, because that's like the hardest thing to solve. The gas station also sees the Toyota, and we were told that fact right from the beginning of the problem. So here at the bottom, I can do this gas station bird's eye. From the perspective of the gas station, I can draw vectors for what it sees. It sees 2 vectors. It sees a Pontiac and it sees a Toyota. So what it sees are VPG, right? This is from the perspective of the gas station, VPG and VTG. I have a vector for PG that I just figured out, and a vector for TG that was told to me at the beginning of the problem, right? So this would be like the bird's eye of what the gas station sees. I could do a similar one for each of the other 2 objects. Sorry, I can go back to that in a second, but I only have 2 minutes. Say I do a bird's eye for the Pontiac now. I probably won't have time to do the, if you want right away at the beginning of the next class, I could do the other one. But if I do the Pontiac, then first of all, I'll do a vector for the VGP. Like both my vectors are going to be like blah P if I do from the Pontiac. So this is the Pontiac bird's eye. Oh, I shouldn't draw this like this. So first of all, I have VGP. Well, it'll be 82.6 at 3.1 degrees northwest, right? Like it'll be like this. VGP equals 8.4 at, and this is not really drawn very well, but at right, it's just the reverse of VPG. And then there will also be VTP. And VTP is southwest. VTP would be something like this. Right? This would be the Pontiac. I mean, this would be the bird's eye view from the Pontiac. The Pontiac sees 2 things. It sees a gas station and a Toyota, both from its perspective. So they're both going off like this. And I'll leave it to you to do the third one, which would be VTG. Oh, sorry, we already did G. The third one would be like VPT and VGT. And if you, and you'll know you've done it right. Okay, I know it's 4:20 now, so I'm putting down the cannoli and I'm putting down the gun. If you do the third one, the third bird's eye from the perspective of the Toyota, you'll know you've done it right. When you stand back and look at it, and if you complete these 3 triangles, each of them, you'll realize all 3 triangles must be the same. It's just that it's the same triangle, just rotated different ways. And you're just drawing 2 different sides of it each time. I can't say that any better, but if you do the third one on your own, you'll know you've got it right. When you stand back and look at it and realize that it has no sides that you haven't already done in one of the other 2 triangles. I'll leave it at that. But all right, again, all of what I just did, for anybody who's tuning in and out, all of what I just did was, in effect, the free float problem in your practice exam. If you go back and try to do the free float problem, hopefully you'll see that this all fully shows you how to do that. Okay, sorry. So if that's funny. All right, fair enough. Oh, okay. I see Chris's comments. Okay, I'm laughing. But I'm stopping. I'm putting down so have a very nice night. Study, and look at the practice exam. Come with specific questions for the practice exam Wednesday. I'll try to I won't, what I do, I'll try to prioritize what you ask. And what I don't do, hopefully we'll do in the other class, blah, blah, blah. So you can go, but I'm standing here for a second. If there's any questions or anything, I'm here, and I'm turning off the recording. Okay, thank you. Yes, have a good day. Thank you. Awesome. Thank you. Bye.